Hello and welcome to Aditya classes. Today we'll take up a question that was sent to us by a fellow learner. He wants us to solve this using dual-simplex. Now in previous lecture we took up a case of dual-simplex where we had a problem of optimization, that is Z-max. This time we are going to optimize it for a Z-min. So this is Z-min 4x1, 12x2 and 18x3 and these are the constraints. And then there is another constraint, obviously x1, x2 and x3 should be greater than equal to 0. Today we'll try to solve this using dual-simplex. Now because we wish to solve this question using dual-simplex method, we'll convert these inequalities into less than kind of inequalities, thereby changing our problem to Z-min is equal to 4x1 plus 12x2 plus 18x3 and multiplying complete equation by minus 1, I will get a minus x1 minus 3x3 less than equal to minus 3 minus 2x2 minus 2x3 less than equal to minus 5 x1, x2 and x3 greater than equal to 0. Now, if we see here, what I have done is, I have converted the inequalities into less than kind of inequalities. But I have left the optimization function as minimum only. I have not converted that minimization into maximization. What some books, some lectures would suggest you is that you can multiply this also to minus 1. In that case, what it becomes is Z max is equal to minus 4x1 minus 12x2 minus 18x3. So that is also a possibility. This kind of constraint, this kind of optimization function we had in last lecture also. Today we will test what happens if we leave it to Z-min only. If you leave it to Z-min only, then also there are no issues. Instead of Cj minus Zj, I will be taking Zj minus Cj in this case. That is the only difference. Otherwise, same process will be following. Outgoing variable will be decided from most negative, incoming variable will be decided from minimum positive from Zj minus Cj. Because if we go ahead and solve minimization function, then there will be alterations in both of these. Now because we have learned the simplex in such a way that there is only one difference between minimization and maximization for our method, that is Cj minus Zj or Zj minus Cj. Remaining everything is same. So let us go ahead and convert it into standard form. The standard form would be minus x1 minus 3x3, then there will be a plus s1 is equal to minus 3 minus 2x2 minus 2x3 plus s2 would be a minus 5. S1 is added here, S2 is added here, hence we need to bring them into objective function also. Z-min is equal to 4x1 plus 12x2 plus 18x3 minus 0s1 plus 0s1 plus 0s2. This becomes my standard form. Now can we have our IBFS? IBFS would be from here. S1 is equal to minus 3, S2 is equal to minus 5. Now the problem is this is not IBFS. This is initial solution but not feasible. So this was dual-simplex. Converting constraints to less than equal to standard form. Now let us go ahead and solve this. If we prepare our simplex table, we see that we have B, S1 and S2. S1, S2, X3, X2, X1, S1 is equal to minus 3, S1 is equal to minus 3, S2 is equal to minus 5, Now because it is dual simplex, it is taken as IBFS. If it were simplex, this would not have been our IBFS. If it were simplex, negative start is not allowed. So for simplex, it is not an IBFS, but for dual simplex, it is our IBFS. It is giving S1 is equal to -3 and S2 is equal to -5, coming from what constraints? -1, 0 and -3, 1 and 0, 0 and 1. Then we have a -2, -2 and 0. What are the contributions? 4, 12 and 18. 4, 12 and 18. Then we have a 00. These are CJs. We can have our ZJs. Because we are starting with S1 contributing 0, S2 contributing 0. We'll be having all these values as 0. Then because it is minimization, I'll go for Zj minus Cj. 0, -4. -4, -12, -18, 0 and 0. Now these negative or 0 values indicate that this is optimum solution. But these negative values indicate that this is not a feasible solution. Why feasible solution? Because I need all values to be greater than or equal to 0. Some of my variables are coming as negative. Although these are not x1, x2, x3, these are not decision variables, but these are basic variables. These form the part of my basis. So I go ahead and make use of dual simplex. What is the formula? What is the algorithm for a dual simplex? Outgoing variable is decided as most negative b. Most negative b is here. I get my key row. Then our incoming variable is decided from minimum positive from Cj minus Zj. Now because I am solving a minimization problem, I'll make it Zj minus Cj. For Zmin. Because I am doing Zmin, I'll convert it to Zj minus Cj. Zj minus Cj divided by Aij. This is my key row. -4 divided by 0 would be infinite. I need minimum positive. -12 divided by -2 would be a, it will be a 6. -18 divided by 2 would be a 9. You can leave this, you can leave this. So what do we get? This becomes my key column, key element. Can I divide all these elements by -2? x1, x2, x3, s1, s2. 4, 12 and 18 contributions, 0 and 0, b. S2 is outgoing variable, x2 is incoming variable, s1, x2. Contributions of s1 are 0 and s2 is 12. Divide all these elements by -2, making it 0, 1, 1, 0, minus half and minus, or rather minus will cancel out, we'll get a 5 by 2. 5 by 2. Key row has been transferred. Now I need to transfer my first row. That will be -1, 0, -3, 1, 0, -3. What is the formula? Old row minus key column element I multiplied by modified key row is equal to old row. We have our old row. This is the row that we need to transfer. Key column element I. This is my key column element I is 0. Now, because it is 0, whatever I put here becomes irrelevant. Hence, we'll get the same row as this. 0, 1, 1, 0, minus half and 5 by 2. Giving me -1, 0, -3, 1, 0 and -3. We have -1 0, -3 1 0 and -3. Can we have our Zj? We have our Cj, we can have our Zj. This all will be multiplied to 0 at some point of time, so we can leave it. This will be 0, 12, 12, 0, -6. We need Zj minus Cj. Zj minus Cj would be -4, 0, -6, 0, -6. Then all zeros and negatives are indicating that this is optimum solution, but a negative in basis is telling me that it is not feasible. We have an optimum solution but not a feasible solution. So we again take up this ratio Zj minus Cj upon respective A, which will be my key row. Most negative is my key row. This is the only negative, so this becomes most negative. This is my key row, Zj minus Cj divided by respective Aj. So that ratio, the theta that we used to calculate over there, this time it becomes Zj minus Cj upon Aj. So this will be 4, 0, 6 by 3 would be a 2. We'll have a 0 and infinite. I need to pick minimum positive. Minimum positive is this, giving me my key column. So I have my key row, I have my key column, I have my key element. So can we start with our next table? What is happening over here? S1 is outgoing variable, x3 is incoming. So I have x3, x2 is still intact, x3 giving me a contribution of 18, 12. This is key row, so I need to divide it by -3, divide all elements by -3, thereby getting 1 by 3, 0, 1, -1 by 3, 0 and 1. Now let us transfer our second row also. The transfer would be 0, 1, 1, 0, -half and 5 by 2. I hope you remember the formula. It is old row minus key column element I multiplied by modified key row is equal to new row. Key column element I. Key column element I. Modified key row is here. We have a 1 by 3, 0, 1, 1 by 3 and 0 and 1, making it 0 or rather -1 by 3, not 0. -1 by 3. This will be 1, 0, 1 by 3, -half, and 5 by 2 is 2.5 minus 1, 1.5. Remaining we have -1 by 3, 1, 0, 1 by 3 and -half. Can we have ZJs? It will be 6 minus 4, giving me 2. 6 minus 4, 2. This will be 12, 18. That will be -6 plus 4, giving me -2. That will be -6. -6 plus 4. Let me go for Zj minus Cj. -2, 0, 0, minus 2, minus 6. Once again, all values are 0 or negative in net evolution row, telling me that this is my optimum solution. B is 1 and 1.5, telling me that this is also a feasible solution. So, now I can say that I have my feasible optimum solution. What is that feasible optimum solution? Can we remove this and frame it over here? It is x1 is equal to 0 because there is no x1 in the basis, x2 and x3. x2 is 1.5, x3 is 1. 1.5 and x3 is 1, giving me a z min of 4x1 plus 12, x2 plus 18, x3. 4 multiplied by 0 plus 12 multiplied by 1.5 plus 18 multiplied by 1, making it 0 plus 18 plus 18, making it 36. This is my optimum feasible solution. This is optimum also and feasible also, as all the variables in basis are positive. All the variables in basis should be either 0 or positive. So this is our second attempt at dual simplex. This time we took a minimization problem, though we were interested in solving it using dual simplex, so we converted the constraints into less than types. But still, we kept the objective function into minimization only. The only difference that maximum and minimum makes is whether it is Cj minus Zj or Zj minus Cj. So, hope these two lectures help us clear some doubt on dual formulation and dual simplex. Dual simplex is an algorithm. Dual formulation is only formulation. The formulation that we have studied in 5 steps. When we started this journey of linear problem formulation, we studied a formulation of 5 steps, where first step was identify the objective function. Second step was identify the decision variables. First step was identify the objective variable, key variable. Second step was identify the decision variables. Third step was identify the objective function. Fourth step was identify constraints. Fifth step was non-negativity or physical constraints. So that was a formulation of linear problem for subjecting it to simplex. That was a formulation of linear problem for subjecting it to simplex treatment, simplex algorithm. Similarly, that formulation could have been done in a different perspective, a different way. That way was called dual. This is the original way to formulate a problem. Hence, it is called primal. The other one was called dual. Once you have your formulation, then simplex solves it. So, formulation could be primal or dual. There is no simplex formulation. Simplex is an algorithm. Dual simplex is an algorithm. You have a primal formulation, you have a dual formulation. Yes, we do not call it primal formulation unless we study dual formulation. But that formulation is primal. That is a primary formulation. So, we have a primal formulation, dual formulation. But both are solved using simplex. This is dual simplex. This steps in, this is used when we are getting an optimum solution. Everything is 0 or negative, but a non-feasible solution. And the difference between two algorithms is that in simplex, we used to get our incoming variable, and then after dividing B by incoming column, we used to get our outgoing variable. Here it is something different. There we used to pick the most positive from here and least positive from theta. This was the idea. Here it is different. We take most negative from the B and minimum positive from Zj minus Cj upon Aj. The ratio of Zj minus Cj upon respectively Aj. Minimum positive. Yes, if it is a maximization case, it becomes Cj minus Zj upon Aj. So this was it. This was a summary of dual simplex method. Next time, we'll meet with some more problems, some more topics, some more issues related to simplex, like integer programming. So for now, we'll take a break. Thanks for watching. Bye-bye. Take care.